on to chapter 7, which deals with the first part of chapter 7. We're going to do two parts of it, but the two sets of slides for it. But the first part, because we did in 6, was just kind of talking about convection and the basis, right, of where the convection comes from. Okay, and with the boundary layer thicknesses. Now we have a situation. It's external flow. Okay, so chapter 8 deals with internal flow. So that's like flow through a pipe internally. And this chapter deals with external flow, and this section 7.1 to 7.3 is a flat plate, okay, with external flow. All right, so a little bit of review here. We have the boundary layer thickness. Okay, here's in laminar section, and then we hit a critical point, critical distance, and we go to turbulent here. Okay, and we use the Reynolds number to distinguish where we are. Okay, with Reynolds number less than that critical is laminar, greater turbulent, right? Well, and we use this as our parameter for that critical. That Reynolds number is our critical one. Okay, but we can have a situation where it's all turbulent. Okay, so if we had a flat plate like this, but we tripped the flow at the beginning, okay, or had some surface roughness, tripped the flow, then this would all be turbulent. Okay, and that would mean the whole flat plate is turbulent, and then we could utilize looking at it all as just a flat plate with turbulent, versus if it wasn't and tripped, then we have this flat plate is transitioning. It has laminar section and then turbulent, so we would have to kind of average together these different things to get an average convection coefficient, say. When we look at these flat plates, we have two situations. Okay, we have uniform surface temperature, or UST. Okay, and then we have uniform heat flux, which is uniform surface flux. Okay, and that's in the case on the flat plate. It's on what's happening on that flat plate. Are we putting a constant heat flux out? So are we just putting the heat flux, maybe it's a heater, or are we keeping that plate temperature constant to a set temperature? So we have those two different situations. Okay. One other thing that can happen is what you see down here is that the thermal boundary layer thickness doesn't have to start at that leading edge right here. Okay. Here the velocity does, because it has friction, and there's the velocity ends up being 0 on that surface right there, so it automatically starts creating the velocity boundary layer thickness. Okay, but the thermal boundary layer thickness in this situation didn't start until right here, because T infinity is the same as the T surface. If these two are the same, there's no boundary layer that can be created that has a thermal boundary layer that has the different temperature or temperature profile from one to the other. So there's no thermal boundary layer thickness. Here, all of a sudden, now is a situation right here where we have this uniform heat flux. So now the temperature, in this case, is greater on the surface than T infinity. So that will start the thermal boundary layer thickness. Okay. Or if there's, the temperature of the plate is always T infinity, then there's no thermal boundary layer thickness being created. Okay, so that means we have this kind of entrance distance here that you see. All right, so one thing in the couple slides here is, and I'm not going to go into a ton of detail, but what they do is with a dimensionless similarity parameter, and that is just a parameter because we know the velocity distribution and the temperature distribution are the same kind of the velocity distribution will look like this. And, at small thicknesses, it's just a scrunched version of it. Okay, at large thicknesses, it's like a expanded version of it. You're just expanding it or compressing it. So because it has that same shape, they utilize that. Okay, and that's what this parameter kind of does in the solution. So they're solving those boundary layer equations that we created in the chapter 6 for this special case of an isothermal plate, laminar, constant property flow. So they set it up with the substitution of this parameter here, and then they solve. So they solve for the x component velocity and the temperature distribution. So here we have our flat plate, right, and our velocity distribution, generalized. But here's the actual one from those boundary layer equations. They've solved it, and this is the flat plate's profile. And we know if we have the velocity profile from our first example in chapter 6, we can solve for the friction coefficient, right? If we have that. We just utilize that and take the derivative at y equals 0, right? And then also from the solution of this equation for the temperature part, so this was for the velocity part and this is for the temperature part, we can get the temperature distribution. And that is what you see here. So here's that Prandtl number of 1, which we know Prandtl number 1, the boundary layer thicknesses are identical from our other example, right? And that you see is the exact same shape you see over here for Prandtl number of 1. Now, if you change the Prandtl number, it looks different, right? So lower than 1, that's what you have here. So lower than 1 would have been like air that we have in that example problem where the boundary layer thickness for the thermal is greater, which is what you see occurring here. And then a Prandtl number higher than 1, so in this case 7, is being shown as a lower thermal boundary layer, and that's what you see with this. And we have a profile again. And with that profile means we can take the derivative and at y equals 0, use that to get our convection coefficient. So this is an exact solution then. And that's what we're going to do right here. So first off, we are able to see how that boundary layer thickness for the velocity gets bigger. So it's just a function of x, so location along that flat plate, and then the Reynolds number at that location. And we can basically, with that, draw what that boundary layer is going to look like just off of that equation. And then what you see here is they're doing what we did in our first example, right? Getting that shear stress and then plugging that into here. Like we did in the first example, it just has a little bit more substitution, so it looks a little bit more wonky, technical term, but it's doing the same idea to get that derivative and it's setting it at y equals 0, and you end up with that equation that is just a function of Reynolds number. And this is our local. So at a point, right, at x, some point right here where we have what that friction coefficient is, or at that point. And then utilizing the equation we have for the convection coefficient that we did in the first example too, we again have to get that partial, set it equal to 0, or at y equals 0, sorry, not set it, and solve, and you see again lots of different substitutions that are occurring, but the same idea is we can end up getting what that value is and utilize it, and that's what they do here to get the Nusselt number, which is this. So we get a Nusselt number and that's being utilized for basically we can utilize it to get our convection coefficient. Okay, and you see it's a function of Reynolds number and Prandtl number, right? And at some location X. And that's what we said in chapter 6, that the Nusselt number is a function of Reynolds number and Prandtl number and location. Okay, so that's exactly what we have. And this is the local, again, because it's at X, some location. And then from this boundary layer solutions, we also get the equation that was kind of given to us in the other example right there. Okay, so it comes out and has that Prandtl number of 1/3. All right, so that's local. What if we want the average, right? We want it over that whole flat plate, not just at one point. Then we got to integrate over the flat plate, and that's what's being shown here. Okay, so the average, you integrate over that flat plate, and you get the over that whole flat plate's friction coefficient, and over that whole flat plate, you get the Nusselt number. So this is our average, right? The one thing that's occurring is we need to get properties, okay? So in Reynolds number, there's density, there's dynamic viscosity, or there's kinematic viscosity. Prandtl number is a property, okay? So where we get those properties, what temperature is, we use what's called the film temperature. And that's just taking the average of the surface temperature and T infinity, right? If you're a flat plate, say, and there's our thermal boundary layer thickness. Out here it's T infinity, right here it's T surface. So we're just kind of taking an average between those to grab our properties at, okay? Because it's transitioning from T surface to T infinity. All right, so for turbulent flow, we have in local, so this is local right here, empirical coefficients. So that means that was from experiments, okay? So there's not an analytical solution to the boundary layer equations for the turbulent. They do experiments and measure it directly. Okay, so in that case, we get these, okay, for the friction coefficient and for the Nusselt number at the local. Okay. Average, though, so this is now average down here, has two cases when you have turbulent flow. We have case 1, case 2. The first case is where we have a transition. Okay, so that's when it's going from laminar to turbulent. That means we have to integrate, have the laminar up to that critical length, and then turbulent convection coefficient afterwards, all the way to L. Okay. So in that case, when we integrate, we get these two equations. Okay. And then the bottom one, the second case, is if it's tripped flow. So that means it's just turbulent the whole time. Okay, so then we get the equations here. Okay. All right, special case, like I mentioned in the first slide, is if we have the unheated starting length, like we had right here, right? There's no temperature difference from here to here, and the temperature difference starts here. So that means we have this unheated starting length, Okay, so what do we do in that case? And that's what's being shown here. So this is what we do to get that, okay? We have our two cases, uniform surface temperature. So here would be uniform surface temperature, or we have uniform surface heat flux. So, or this would be a uniform heat flux condition, so a heater or something like that there. All right, so what we do for that is we have these two equations, right? We get this one, okay, and the parameters are here, okay, and it has the situation of laminar, and then surface temperature, surface heat flux, surface temperature, surface heat flux for turbulent. Okay, and we have all these different coefficients dependent. Okay, so C, M, and then our, the starting length is here, and then X and AB. Okay, so this is local, right? This is to get the local Nusselt number. Okay. If we want to get right here is our average, right? Because you see the bar. Okay, that's telling us average. And we have to use those equations. Okay. And at film temperature. Okay, so this is with a uniform surface temperature after the starting length, and this is if at the uniform surface heat flux after that starting length. All right, so then an example. Okay, we got 7.17. The top surface of a compartment consists of very smooth A and highly roughened B portions, and the surface is placed in a atmospheric airstream. In the interest of minimizing total convection heat transfer to the surface, which orientation, 1 or 2, is preferred? If the temperature of the surface is 10 degrees Celsius, T infinity is 35 degrees Celsius, and the free stream velocity is 25 meters per second, what is the rate of convection heat transfer to the entire surface for this orientation? And then they give the schematics you see up here. Okay, so we have smooth surface A, okay, and then we have rough surface B. And they want to decide whether they want A first, right, or B. Basically flipping it around and have B first. Okay, but they want to lower the heat gain, right? So lower the heat gain. So minimize convection heat transfer. Okay. So we're going to have kind of these two situations, right? If it's the rough is first, you can kind of see from the assumptions, we're going to assume that it's tripped, okay, the boundary layer. So then if the rough is first, it's turbulent throughout, okay? Okay, that's condition 2. And then if smooth is first, we're going to have transition, right? So it is going to go from laminar to turbulent. Okay, so which orientation do you think is better to lower the heat gain? Any ideas? So if we want to lower convection, which in this case, the temperature of the surface is always the same, right? Convection is H P, let's say we have T infinity minus T surface, okay? And the area is always, so we'll just do heat flux. All right, the area is the same either way. So these temperatures are the same. So we're really just trying to see what the convection coefficient, which one's going to be lower. Do we think the one with laminar and then turbulent, or the one turbulent throughout? Which one's going to have the lower convection coefficient?
Maybe the laminar first, because I feel like the turbulent will promote more mixing of the fluid.
Yep, yep. So the turbulent, because it has, you know, when you think about, you know, what this looks like, you know, you have this in the laminar section, you have these nice, you know, streamlines, okay? In the turbulent section, you know, it's this hectic, crazy flow. So it does a better job of, you know, moving fluid from the bottom to the top or top to the bottom, so it then will transfer heat better, right? Where these kind of streamlines don't promote it as well, right? Then the high mixing, that high inertia. Okay, so that's this one then, right? So that would be, we can also check them. We can solve for both situations and just see which one's better too. And that's what's going to be done. All right, so we know we need to get the convection coefficient, and we're just basically going to get it for the two situations. Tripped, which is turbulent, so that's the tripped. All right, so we know we're turbulent, so we go to our cases. We don't have an unheated starting length, right? So it's all the same temperature throughout. Okay, so we go to our turbulent situation right here, and we have the transition situation for Nusselt number, and we have the trip situation for Nusselt number. So it's those two cases that we're looking at which require Reynolds number, okay? All right, so then we can get Reynolds number by grabbing our properties at the film temperature, okay? All right, so we get our Reynolds number, boom, we got Reynolds number, right? And we could also get the distance, the critical distance for when tripping would occur, because the Reynolds number would just be X critical, this, and we know our Reynolds number for tripped, right? So way back here, 5 times 10 to the 5th is that for trip length, okay? Ooh, went too far. Okay, so that, if we solve for then the X critical, we actually get 0.31, which is, in this case, you know, it's 0.5 here and 0.5 here, so that means it's going to already trip, you know, somewhere around here, okay? So that means the roughness is not going to force the tripping. When it hits here in the surface roughness, it'll already be turbulent before then, okay? All right. So then in our transition case, solve for the Nusselt number, the average Nusselt number, we get 2270. If we did the fully tripped case, okay, the fully tripped case is what you see right here. And so this is our transition. Here's our fully tripped. Okay. And see the tripped is 3050, transition was 2270. The higher Nusselt number correlates to a higher convection coefficient. Okay, so we saw the transition is lower. Okay, so we can just use the Nusselt number is equal to HL over K, right? K of the fluid length, and we can use that to get our convection coefficient. And we can plug that in to our Newton's law of cooling. Okay, so if we had this problem in chapter 1, they would have given you the convection coefficient. Now in chapter 7, you're figuring out the convection coefficient that you need to use, right? So you don't know this convection coefficient in Newton's law of cooling. You're figuring out which one to use and to get that value, okay? Area was the same. This was the same between the two configurations. So we get 739, and the other one would be, you know, the ratio of, you know, you just put in the ratio of those two Nusselt numbers, and that would tell you how much higher the other one would be. All right. Any questions on that? All right, so we're running out of time, and there's one more in here, and then we have another section of slides for next class for chapter 7. But I'll leave it at that. Is there any questions you have for me beyond this?
When will you be posting the exam solutions?
I'm gonna try to do it right after class ends. I gotta scan them in and put them up online. So I'm gonna try to do that right after this. Yep. Anybody else?
Yeah, sir. So the homework for chapter 7 is due the 2nd.
The second, maybe, for chapter 7.
Are you gonna change it or is it gonna stay the same?
Is that, which day of the week is that?
I think Tuesday.
I might keep it the same. I mean, because we'll be done with chapter 7 next class.
Okay, thank you.
For sure. Yeah, with the slides and the example problems, we'll be done with chapter 7 next class. It will definitely not bleed over. Okay. Any other questions? All right, then that's it for today. You guys have a good rest of your week, and if you have any questions, don't hesitate to contact me. And again, I said I saw some emails. I haven't had a chance to look at them yet, because I was trying to get the exam graded and out to you. All right, you guys have a good weekend. I'll see you on Monday.
Thank you.